Okay, it gives me great pleasure to be able to introduce our next speaker. I've had the good luck to be at 2 organizations where Dave Katz has worked, and in fact, he's the perfect person to talk about why are we scared of SPF. He's always been very good to those of us novices. When I first started at Merit and actually thought that an EGP was my monogram, he was very kind to explain that no, that was really a protocol, not just my initials. And so I think it gives me great pleasure to introduce him. Dave's been at Merit, Cisco, Juniper, Frank Allison and the Odd Sox, and he's now going to speak to us about IGP scaling and stability.
Thank you, Elise, and good morning.
Good morning.
Hi. I'm going to talk a bit about the history of IGP and IGP implementation in particular, because there's the spec and then there's the reality. Talk a bit about how, what happens when IGPs converge, what are all the pieces and where are all the weak spots, and finally some conclusions. If you go back to about 1990, it's when we first started seeing implementations of link state protocols, ISIS and OSPF. The first couple of years, we're just trying to get the implementations to work. These are not trivial bits of code to write. And if you hadn't done it before, achieving some kind of sense about how things worked was pretty difficult. You have to work through the implementation before you really understand the protocols. And so the early implementations had enough trouble just calculating the right routes without spending a lot of time and complexity trying to figure out how to make them work in larger networks. So a lot of prototype quality software was shipped, and anybody who played with routers early on, sounds like I'm cutting out here, anyone who played with routers early on knew that if you push things hard enough, they'd fall over. When we got to about 1994, things got a little bit more stable, and so fast convergence became a marketing, a marketing point. And the interop booths at around 93, 94 had a lot of people unplugging cables and showing how rapidly their protocols converged. It was all very exciting, but it didn't really matter a whole lot in those days because a network converged fast enough if it was backed up before anybody managed to call the knock. So the time frame was a minute or two, and when you really did try to turn up the heat a little bit, things kind of flapped around wildly and fell over. Then 95 came around, and this idea of this commercial, large, international internet thing started happening, and it really did have to work. You didn't want the network to fall over. Those who are old enough remember AOL down for 19 hours, and there were lots of other ones that perhaps got a little bit less press. But there was considerable pressure to just make it stable. We don't really, we'll deal with 1-minute outages in return for the thing not burning down. So as a result, lots of timers got cranked to really big values. So adjacencies would stay up for a minute before they'd go down and that sort of thing. And the one thing that was, the piper was paid with convergence speed. We traded that off for stability and scalability. But now there's pressure to converge more quickly again because there are actually applications that care. Voice over IP is an example. There's also considerable pressure, technological pressure. There's a perception that IP is slow to converge, and therefore we need ATM or we need MPLS or we need whatever. But we've learned a few things over the years, so I think we know a bit more about how to be fast, even with traditional IGPs. So there's, in my list anyhow, 6 pieces to your IGP converging, or things that have to converge after your IGP changes. The first thing you have to do is detect that something changed. And if your hardware does this for you, life is good, because you know, when the light goes out on a Sonnet link, you can groom that in hardware, you can groom that in drivers, you can get whatever level of you know, rapidity and hold down and debouncing that you want. One issue with this, we're increasingly seeing Ethernet technologies in POPs, and as of this point, there is no, you know, data link layer signaling that cleanly tells you that you can't talk to your other neighbor. If the wire falls out of the back of your router, you can tell that that happened. But if the wire falls out of the other router, you can't tell that that one router went away. So ultimately, you still have to fall back to software failure detection using hello protocols. And in the past, you know, the only way you can get a rapid detection is to rapidly send hellos and rapidly time out when you don't see them. In the past, attempts to do this have made things fall over pretty badly because, you know, the scheduling latencies in the protocol implementations were, you know, on the same order as the timeouts. So if you run off and, you know, calculate SPF for 2 seconds, or you type a show command and the CPU goes away for 2 seconds and all of your adjacencies time out, life is not good. You can now, and you know, there are several vendors I know that are now capable of doing this. You can do fast hellos, and even somewhat scalably, you know, sub-second timeouts and hundreds of neighbors. And to do this, you need to change the scheduling model, and depending on your hardware architecture, you may actually distribute the processing of these things as well. You still have an issue of, you know, if you ultimately all you can do is send and receive hellos at full speed, and can't do anything else, then things will start to fall apart, although you can get clever. But the big point is, the first thing you have to do before anything else is make adjacency maintenance stable, regardless of the load on the router. So this, oh, the router's at 100% CPUs, it's starting to drop adjacencies, just shouldn't happen. Now, once you've detected that something has changed, you have to tell the world about it by sending an LSA or an LSP out. Traditionally, when a router detected a change, there was a hold down period. First to try to collect multiple changes because you were only going to get one chance for a while to send a new packet out. So if a couple of things changed, you wanted to group them together. And then there was a hold down applied where once you've generated an LSA or LSP, you don't regenerate it for a period of time, typically on the order of seconds, in order to put an upper bound on the amount of traffic that a router can flood into the IGP. This obviously has issues with convergence time because you're withholding information that the rest of the network needs to know in order to converge. So a more intelligent strategy is to more rapidly announce interesting things that change, and interesting is a heuristic that people can figure out on their own. But to allow yourself to more rapidly generate LSPs or LSAs, you know, for a while at least, and you still probably want to, you know, eventually put a hold down on things just so that you don't, you know, run the network continuously if you have a flapping link, for instance. There's an interesting side effect if things are implemented intelligently, which is that when the network gets loaded, it can actually become more efficient because the newer information can take over and squash the old information that's in flight. So you can get away with less than, you know, a multiple of the number of packets, even more so when things get busy. The ISI is pretty easy to twist in these ways. If you read the spec literally, there's a number of timers and things in there that say you shouldn't do things faster than, you know, faster than X. But none of those are really normative in the sense that you can tweak those and not affect interoperability. So there's what the spec says and what you really know you can get away with if you know what you're doing. OSPF, on the other hand, the founding fathers that wrote OSPF back in the late 80s decided that the senders of LSAs couldn't be trusted to limit the rate at which they are generated. So the spec calls for the receivers to throw away LSAs if they receive an updated LSA less than 5 seconds after receiving a previously updated LSA, which kind of makes it hard to go any faster than 5-second intervals in changes. So I'm taking the radical step of suggesting that we ignore the spec in this sense, which you can do really without any interoperability problem. If you're talking, if you remove the receive gating, and then you let your transmitter be smarter and go fast sometimes and be adaptive, the receivers that no longer filter things will go fast. The old receivers will still drop the packets, they'll be retransmitted, and things will converge roughly at the same speed they will now. And this is only the case when things are changing rapidly. Or you could add a knob, but I have a slide later about adding knobs. Once you've generated LSAs and LSVs, you have to flood them. So there's traditionally been delays in this process as well, particularly in OSPF, where you don't send individual LSAs, you group up at a hop-by-hop basis whatever LSAs need to be flooded out of a link into an LSA update packet and send that packet. And so by delaying the relaying of LSAs, you can gain efficiency by reducing the number of packets you're sending. Additionally, most implementations throttle the rate at which LSA or LSPs are sent on a link because these protocols don't have any flow control. And so you can overwhelm a receiver. If you have a relatively low-powered router with a whole lot of links on it, you can swamp them with incoming packets. And most implementations have all kinds of heuristics, particularly when a router first comes up, so that all of its neighbors don't attack it with full LS databases and so forth. But all of these things directly affect the rate of convergence, because if it takes, if there's a latency of 500 milliseconds per hop, then it's going to take 500 milliseconds times the diameter of the network for the information to propagate all the way across the network. Furthermore, even when things aren't changing, there's background rumble in the LS database. There's typically they're being refreshed at various intervals, and depending on the implementation, you may have bursty refreshing going on, and all those packets get in the way. And if you're doing throttling, you may have a whole bunch of other LSAs which aren't really interesting in front of you on the queues. So you can, if you start looking at the scheduling of the transmission of LSAs and LSPs, and give priority to the interesting ones, and where interesting is once again the heuristic, you can get the one signaling your changes through quickly. The retransmission schemes are typically fairly bare bones. Many implementations simply retransmit LSAs at a fixed interval, but unlike transport protocols, this is a retransmission per packet, and if you have 100 packets that are awaiting retransmission or being retransmitted, you'll have 100 packets being sent every 5 seconds. And so depending on if you've just flooded 60,000 LSAs because somebody accidentally redistributed BGP into OSPF, which happens about once a year somewhere, you can end up in a world of hurt. So with some adaptive retransmission, you can at least keep from completely tanking your neighbors. And if you have your scheduling right, the noise LSAs become in the noise. You don't actually have to care about them anymore. And there have been some discussions about, oh, look how much background traffic there is, and we should try to suppress that, and it's scary and bad. And it's good to know if it's pathological, but on the other hand, it shouldn't be a problem if you do things right. Now we get to SPF. Everyone seems to be really scared of SPF, and the reason is that it's caused all kinds of trouble in a lot of shipped implementations. Initially, the implementations were slow. It might take a second or two to run an SPF across a network of several hundred routers. And if you have a run-to-completion scheduler, which most implementations do for arcane technical reasons, if your SPF takes a long time, you may not be sending or receiving hellos during that time, And if you're trying to get your detection times down, you can end up losing hellos, and then adjacencies fail, and so the adjacency failed, so you have to run SPF again, and then you run SPF and more adjacencies fail, and then the network reaches metastable meltdown state, which is really cool if you're not running the network. It's like a good train wreck. It's fun to watch from a distance. So there's all kinds of hold downs and scheduling delays and SPF delays and so forth that you'll see commands to control. And these are essentially workarounds for these stability problems. But of course, these slow convergence, and there have been presentations here in the past demonstrating that it may take 2 or 3 of these intervals to finally really converge and get rid of all the routing loops, because until everybody has calculated SPF on the final set of LSAs, then there's going to be inconsistent routing in the network, and packets are going to run in circles and fall on the floor. So the key here is, if you engineer things right, SPF should not be destabilizing. You should be able to run it all day long, constantly, without hurting anything. The first thing you have to do, as I mentioned in an earlier slide, is do adjacency maintenance in a preemptive fashion. Adjacency maintenance has to run in parallel with everything else. So then you don't care how long it takes to run, at a first order level, you don't care how long it takes to run SPF. It's not going to make your adjacencies fall down. If you prioritize things such that even if you're running SPF constantly, you're still in between SPF runs processing incoming LSAs and LSPs and updating your database so that you don't lock the database in some state from a long time, from a long time ago, that will help a lot. Overall convergence shouldn't suffer even if SPF is running all the time, depending on how long it takes to run SPF. There's been mention in this forum before about doing incremental SPFs as a way of reducing the runtime. And this, if you can do it in a millisecond instead of 500 milliseconds, that's gravy too. Right now, there's enough other things broken so that in the larger scheme of things, tweaking the SPF algorithm is not that interesting yet, given all the other things that are slow and the size of the networks that are out there right now. If you can field a network with 10,000 routers in a single area, the SPF times will start to matter a lot, but I suspect that we'll be fixing other problems before we manage to deploy such a network. So this is a good step after we fix everything else. There's also been talk about back-off algorithms for SPF calculation, which kind of made me scratch my head a bit, particularly exponential back-off, because exponential back-off is something you use when you have competition and fairness, you want fairness and so forth. If SPF doesn't hurt anything, then you shouldn't be running away from it, because backing away from it, particularly backing away from it rapidly, is going to negatively impact your convergence. So if you engineer things so that it doesn't hurt you to run SPF, then you don't have to go to heroic measures to try not to run it. Now this is actually the biggest problem, and it's not an IGP problem per se, which is BGP is calculating 100,000 routes to where the next hop is the exit router. Then the IGP calculates the route to the exit router and it has a next hop, and then somehow you have to change the next hops of potentially many thousands of BGP routes when you have a change in the IGP. This has been traditionally done in software where SPF runs, you get a new next hop to get to some router at the other end of the network. Then you go running down through your forwarding table saying, well, I have to replace that one, that one, that one, and that one. And of course that grows at best linearly with the number of routes that you have. If you can do indirect lookups in your hardware, suddenly this cost, which is arguably the largest cost, goes away completely. Depending on how your hardware works, you may be able to do this additional lookup, at forwarding time. So the forwarding table says, for this route, the next hop is this exit router, and by the way, the next hop for that exit router is this next hop router. And if you have efficient enough forwarding hardware, you do that lookup at forwarding time, and this no longer is a routing protocol convergence issue. And it's a huge win if you can do it. Now, once you've calculated forwarding tables, then you have to get them into the hardware, assuming that you have hardware forwarding, which most routers that are out there in the core do. The more forwarding engines with separate forwarding tables you have, the more copies of things you have to download. And this can get incredibly expensive, particularly if you are still doing recursion in software, because you may have to download 10,000 routes to every forwarding card when one link changed somewhere in the network. And so the time for your system overall to converge is going to rise, is going to get worse with the number of these engines. We have had a semi-centralized architecture, although we and everybody else knows that this has scaling limitations. So no matter what you do, eventually you're going to have multiple of these engines if you want to build big boxes that have lots of interfaces. And so the answer really is, if you fix the recursion problem, then updating a couple of routes in a couple of dozen forwarding engines becomes pretty cheap, particularly if you spend some time thinking about how that update process works. In the past, stability and scalability have been the big deal. Above all else, because if the network doesn't stay up, as you well know, it doesn't matter how fast it is. This has been arguably successful, at least those of us who are around long enough to remember when things are really bad. And I apologize to anyone who's still having these kinds of problems. Some of the biggest barriers have been outside the IGP implementation per se. There are architectural issues, systemic issues in the router, systemic issues in the network as a whole. As we chip away at these, then thinking about optimizations of the small things like incremental SPFs will become more interesting. You go for the big targets first. We should be able to deliver boxes that can do this fast and do it with stability and do it scalably. And if you do this right, when a system gets loaded down, all that should happen is that convergence should start to suffer, and it should suffer gracefully. You shouldn't have catastrophic collapses. You shouldn't have sudden falling off the cliff in convergence. And it's not easy to do this, and I won't claim that we're there yet, or that any vendor is there yet, but that we know how we're getting closer and closer to this ideal. And IGPs aren't inherently unstable, which they've sort of gathered a reputation of being so, mostly because of the quality of the implementations over the years, of which I have to admit to having tampered with most of them. So that's why I'm wearing dark glasses. You won't recognize me. If you get to the point where you're just swamped in hellos and you can't do anything else, then things may fall apart. But then you could even get clever and start turning off interfaces or other things, really gratuitous bad things that are better than the whole router and the whole network falling over. You just start randomly losing topology instead, which probably isn't a lot better than a collapsing network, but gets close. Adding more knobs isn't the answer. I've seen some presentations of which there's proudly proclaiming we have these great knobs with 4 values that you can tweak, but no one really knows how to set those values. And Dave Oran has a law that says all knobs have one setting that works and all the rest don't. He says it more succinctly than I do. Most of these settings are wrong, and pushing the responsibility for stability back on the operators by providing knobs like this is not a good way to achieve stability. I mean, I don't know how to set the knobs, so I don't know how I would expect you people to do so. So basically, you either have to make things adaptive so that the routers and the implementations are resilient enough to sort of sense what's going on and adjust the things that need to be adjusted, or better yet, you try to do the implementations in such a way that the values of those parameters don't really matter in the stability sense. If SPF can run all day. You don't care what the scheduling interval you set for SPF is. And if you do have adaptivity, keep it simple and keep it bounded, because the network is chaotic enough as it is, and trying to debug a network which is sort of out there turning its own knobs in interesting and complex ways is going to be really hard. And that's my talk. Thank you. Questions? I may get you out to lunch early here if we're lucky. Oh. I see somebody moving.
I just want to make one comment. First, I enjoyed your talk. Thank you.
Thank you.
And about the incremental algorithms, you're absolutely right. For example, the times that we have presented in the last monologue, the full SPF took like 3 milliseconds and the incremental took like less than 100 microseconds. Yes, it is 2 order of magnitude faster, but 3 milliseconds is already very good.
Right.
But one thing that it wins in the longer term is scalability.
Yes.
As the size of the network gets bigger and bigger, that 1 millisecond or 3 milliseconds, whatever, goes up much higher, much faster
Yes.
than the incremental
it's
one.
worse than linear.
So it's actually good in the longer term, perhaps not necessarily needed today to achieve sub-second convergence.
Right, and I do agree with that. It's they're really fat targets in the meantime, and tinkering with the SPF algorithm is something that should be done carefully when we're not fighting fires and so forth. But I agree. If we can achieve a network big enough so that the cost of that SPF becomes a dominant part of the convergence time, then I will be really happy.
On the other hand, I think it's good to get ready, and then having a better of everything is actually good.
Yeah, I wasn't trying to say that it's not something that should be done, but on the list of priorities is sort of after a whole bunch of other stuff. Anyone else? Well, I think I've made up time for everyone. Thank you.